So, what is mixing? Mixing is basically a process of thoroughly combining the different materials to produce a homogeneous mix. That is the main function of mixing. And why is mixing important? The purpose that mixing is important, I would like to kind of relate to some examples that all of us in our day-to-day life experience. Let us look at the pharmaceutical industry. In the pharmaceutical industry, it is extremely important to have the right formulation of the active ingredient in the entire process, in the entire month. Because that is what is going to be responsible for the effect that the drug is going to have. And if the proportions are not right, if the concentrations are not right, the effects of that could be very disastrous. A more common process, but equally critical, is in the construction industry. When we mix sand with cement, and have some other materials for giving some properties. Again, if the mix is not right, we can have plenty of challenges and plenty of problems. So mixing in any application is a very critical process, because the mechanical properties, the chemical properties, certain cases, the texture, in food products it could be the flavor, in certain cases it could be the composition. That is defined by the quality of the mix. Don't get your mix right, every other process thereafter. Like you did mention, that the percent of rejection is high, and that can be very expensive. So, rejections and poor mixing. What do we mean by a product which is not well mixed, or which is poorly mixed? It is something which is non-homogeneous, and non-homogeneity could be with respect to a particular parameter. It could be with respect to lacking consistency in the chemical composition. It could be color, flavor, reactivity. So it is extremely important that at the end of the mix cycle, what we get is homogeneous. There is also a difference in the extent of homogeneity when it comes to solid mixing and liquid mixing. Because in liquid mixing, when you draw a sample, the level of homogeneity that you get is far greater than what you would get in what is defined as a well-mixed solid sample. Because depending on the blend structures, depending on the material properties, the levels of acceptance in the case of solid blending are less as compared to what is expected in the liquids. So again, non-homogeneity. What it could lead to? It could lead to a lot of failed batches. It could lead to a loss of high value product. The chemical industry, the pharmaceutical industry, we all have experiences on what a cost of batch could be. And one bad batch could cost quite a bit. So it is estimated that the cost of poor mixing, this is some data which has been pulled out from the Handbook of Industrial Mixing, that the cost of poor mixing is estimated at $100 million per year. So poor mixing can be very expensive. That is the reason why we need to focus on mixing when it comes to any product formulation or development. What are the reasons for poor mixing? As I said, mixing is a science as well as an art. So not everything is there in the books, and not everything can be done by experience. At times you have to try and experiment. But the most common reasons for poor mixing is lack of understanding of material characteristics. A lot of times, as equipment manufacturers, we get inquiries. Please quote for a mixer of such and such capacity. Okay. The type of mixer is this. And that is not enough. That is not enough. Because it is not like a kitchen mixer where you can probably put in whatever you want and get whatever you want. No. You have to be very, very specific on the material characteristics. Like you could have materials like solid powders, which are very, very heavy. You could have materials like waste that can have its own challenges, and you can have materials for coating. So the thing is that the same mixer may be used for all of these three applications. But the three applications are very, very diverse. So understanding the material characteristics is the most important thing before we start looking into any mixing challenge. The other thing is that the mixing objectives are not well defined. What is the end point of mix? What are we trying to achieve? What is our desired state? A lot of times that is not accurately defined, and again it is somewhere due to lack of understanding of the product or the characteristics. A lot of times incorrect selection of mixer. I mean that's the tool. That's the tool which is going to convert your raw material into a finished product. It is very, very important that the selection of the mixer is done taking into consideration the material properties. We will look into how, what are the factors which get into the mixer selection. A lot of times, and it happens in the industry, is that a new product has been developed and it needs to be produced. There is a sudden demand. The customer wants the product to be made. Okay, what is the equipment that we have? We have these equipment. Okay, I think this will fit in. Let's try out the process of this. It happens. It happens. So whether that equipment is suitable for the process or not is first to be evaluated. Only then we can be sure about the results. Wrong scale-up techniques. When it comes to applications where you don't have much of a background, much of anything which has been studied, it could again be a challenge to develop a production size mixer. So you would have to conduct laboratory trials. Okay. Take the results from a laboratory trial, bring it to scale up. I will share with you as we move forward an example where how expensive can something like this be, an incorrect scale up. And definitely we all need to update ourselves on knowledge of mixing equipment design. What would be the capabilities of a particular kind of a mixer, what would be the parameters that would get into mixer selection. So it is nothing which is like complex. No, it is all within this, and so long as we take care of this, we should not have any challenges. Now, a wonderful example of how little changes, very, very little changes can make a big difference to a product. Now, this is something which I have experienced personally. So there is this company which is making polymers. It's one of its kind in India. They don't have competition as far as the Indian market is concerned. Now their product was valued at $45,000 per ton, and the product purity that they were having is 90%. The process was set up with some technology which was obtained from China. Okay. So, and what was guaranteed to the customer here, the company here, was that you would be getting 90%. Now, once they were able to establish that 90%, they realized that if they would increase their purity levels to 95, there could be a good jump in the value of product that they would get. They would have a much bigger market. And considering that they were making 55,000 tons a year, the value that they would derive out of this is going to be phenomenal. Phenomenal. So, when this case was presented to us, it actually happened that I happened to visit there. They had a requirement for a new mixer, and I was visiting them for that application. So this company was based outside Mumbai, and after we finished the first lot, I had some time available, and the gentleman who was in charge of the process there made a request that there was a particular mixing challenge that they had. They were working on it, and since we were from the mixing industry, if we could give him any inputs. So it was not something which was, the discussion didn't start with an objective. It was just that a matter of, okay, there is some time, let's look at it. So the agitator here was a 5,500 liter vessel in which they had a polymer, and they were actually doing a washing process. So the polymerization reaction happened. It washed out any impurities which were there in the product. They had a hot water washing process that they would do with the polymer. And the thing is that they were not able to wash the impurities off. That is the reason why 90% was their product purity levels. So they had, if I'm not wrong, they had a 4-bladed pitch blade impeller, and the vessel diameter was about 2000 millimeters. The impeller diameter was 700 millimeters, and the impeller was operating at a speed of around 50 revolutions per minute. The impeller was off-center. So what was happening was that, and it was off-center because we did not want a vortex. When you have an off-center agitator, you do not get a vortex. Vortex was undesirable to the process. What was happening was that because it was off-center, the other side was, relatively unmixed. And at one side they had a fair bit of turbulence. Again, because it was off-center, the diameter of the impeller, was 700. Otherwise, they could have increased the impeller diameter. And by just visually looking at it, it was very obvious that they are not having enough fluid motion. It's a washing process, there is no reaction. So what we are looking here is basically a fluid motion. So there is not enough fluid motion, and that is what is required. There is this portion which is unmixed. The challenge was, how do you, in an operating plant, bring about this change? So the first thing that we looked at, which was very, very easy to do, was they had a variable speed drive which was installed on their equipment. So in a variable speed drive, normally any motor in India is designed for operation at 50 Hz. With a variable speed drive, you can increase the frequency to which it can be operated. You would go up to 60 Hz, that is what kind of, within 60 Hz the motor characteristics don't get affected. You could extend it to up to 75 Hz. So what we did online, on the day that we were there at the plant, is that we increased the 50 Hz to 60 Hz. So with that increase, we did a 20% increase in the mixer speed. So the impact of having increase in the mixer speed is that your power consumption will go up. So before we did that, we had to check what were the power levels being drawn at 50 Hz. Okay. So looking at the motor horsepower, we were well within the limits. And again, because it was liquid mixing, we could, to a great amount of extent, estimate that what would be the power drawn if we are going to 60 Hz. So we increased that, and it was very obvious that with a higher speed, you would have higher turbulence. It was a very simple thing. Okay. Probably because always the production team, are looking at things related to the product. Okay. Simple theoretical concepts often get missed out. We did that. There was an improvement. Okay. As I said, it was visual. It was then substantiated by some test results. The next step, okay, the impeller diameter. Now, the unit where the polymer company, they were very, very dynamic, very, very flexible in their operations. And with a small change in the impeller design that we did online, okay, in the next 1 week, they actually in-house manufactured a new impeller. Okay, and what we did was the 700 mm diameter was then increased. Okay, and it was increased to about 800 millimeters, because that is what 50 millimeters on either side would be accommodated. And then again the results were seen in the improvement in performance. And with just these two improvements, from 90% they could go on to 92%. That was an operating plant, there were no possible changes thereafter. The thing is, what we also did was, again, with the impeller diameter increasing, the power consumption is again increased. So we had to check the mechanical capability of the equipment, and we upsized the motor. We upsized the motor to the extent where it was possible to run the system without making any mechanical changes or any major changes. As we move forward, they had a requirement for a fresh equipment, okay, and that is where we could design the equipment from scratch. So with these two aspects, what we could do is we could increase the level of turbulence. Okay. But the thing is that with increasing the diameter, with increasing the speed, we increase the vortex formation, and that had then to be controlled. And there was also, because the agitator was off center, there was still this portion where the degree of mixing was relatively lower. Okay. So what we did was we had to install some baffles there. The next challenge was it's a polymer company. The product was a very high value product. Okay. They did not want any contamination.
The vortex formation is beneficial for some solid or some semi-solid mixing. Somewhere it's not beneficial.
See, in most of the cases, vortex is undesirable. In most of the cases, vortex is, because it's basically air is getting drawn into the process. But yes, there are certain applications where it is required.
What does it means? It's helping to make a homogeneous mixing or
no?
And
not, because what happens is your entire flow pattern gets disturbed as air gets drawn into the system. So we would come into that as we move forward. We would come into that, but most of the cases, vortex is undesirable. It has to be controlled. It has to be. That is done by installation of baffles. Now, in this case, conventionally the baffles are wall baffles. So they would either get welded onto the vessel, or would be welded onto the vessel, and there would be flats. Now, in this case, because it was a polymer application, they did not want any corners. They did not want any position of the material in the corners, because that would not get washed out along with the batch. That would remain, and that would probably be a contamination in the next batch. So the conventional baffles wouldn't work. So we had to design baffles with low shear, which did not have a corner. And what then came up with the concept of pipe baffles. With all those modifications, when they expanded or augmented their facility, they could get up to 95% efficiency. The solutions were simple. There was nothing which required CFD. There was nothing which required any major change. Just those incremental changes made all the difference. That is when Mixing Expert was formed. That company gave our organization as your company is a mixing experts, okay, and that's where we felt that if in the industry, because besides contributing by supplying the mixers, if you could contribute to the processes and make these incremental changes, it would be beneficial. So that's an example which probably because of which we are all here. Sure.
When we increase the speed,
Yes.
the power consumption increases.
Yes.
Then should we judge it from the amperes or from the kilowatt hour?
See, the thing is, in most cases, you have most plants have an ampere meter. That's the most common thing. So the motor amperage is a good measure of the power drawn. As a thumb rule, in terms of considering that we are operating at 415 volts, we are operating at 50 hertz. As a thumb rule, you could take that the maximum rated current for a motor is 1.5 times its horsepower. So current in amperes is 1.5 times horsepower. It keeps varying, it could be 1.3, 1.4, 1.5. But as a thumb rule, it is a good measure. So if you know the amperage, you can back calculate what is the kilowatt using this guideline. The other important thing is that any motor, say for example, you have a 5 horsepower motor. So a 5 horsepower motor has a maximum rated current of I think 7.2 amperes, somewhere around that range. Now the motor, even if we are running at no load condition, will draw some amperage, right? So in the real sense, the power drawn in the mixing is the difference between the current drawn at the loaded condition less the current drawn at the when it is running idle. The other important thing you have to note is a lot of times you will see that the current doesn't change. These are practical observations. The current doesn't change. The reason for that is that when the motor is being operated under a no load condition, the power factor is low. Power, when we say, anybody from the electrical background will know, is root 3 pi cos phi. So voltage, current and power factor. So motors are designed to operate efficiently at their maximum rated capacity. So if it's a 7.5 horsepower motor or 5 horsepower motor, its efficiency will be the highest closer to the rated capacity. At a lower capacity, the efficiency is lower, so the power factor will be low. So a lot of times that happens, and you can really see what is the power actually required for mixing. So there are a lot of transmission losses which need to be considered when we are designing the system. So as we go further, yes, we will certainly touch upon that.
Sure. See, when you say mixing with a high different bulk density, how do you mix and how you will validate those parameters that it will not decompose at any temperature, or that if you retain that product for longer time, there will not be any surplus of product.
Materials with different.
Okay, now I would like to say, if I say oil and water, you mix it any time, every time, and whenever it is in motion, you will find this mix. But when you stop motion, it will get separated.
Yes.
So what I would say, there has to be some binder which retains that parameter. So I do not know how you are going to correlate that binder with that mixing.
Binder.
Binder means to hold liquid and oil, or any two materials which are of different bulk density.
Yeah,
There should not be any settlement of what.
Yeah, so then see what we're talking about is two different concepts here. Because bulk density is what is relevant to solids.
It is going to be, because see, whatever case we have shown, that maybe having by virtue having same bulk density, so you got better results. But when the two different products, items having different bulk density, how you are going to mix it and how you are going to retain those parameters?
See, the first thing is looking at it at the point of view of different bulk density, which would be applicable to solids. So when you have materials of different bulk density, mixing them, okay, there are different mechanisms of mixing as we will move forward. There is diffusion mixing, there is convective mixing, there is shear mixing. Again, depending on the material characteristics, the principle of mixing which will be applicable. Now when it comes to diffusion mixing is basically Dreidel mixing from the tumbling application. Okay, what you have like the wheat blenders. Now there, because the prime, the force which is acting is gravity. In case of gravity, there is a very good chance of separation. That is the reason when it comes to materials with varying bulk densities, what is used is convective mixing, and what is used is shear mixing, where the materials are very, very cohesive. Second thing is, how do you prevent the segregation? Because a lot of times, if you are doing, if the material is overmixed, it will begin to segregate. That does happen. So in such cases, the final product, say for example, you are preparing a mix of, an example which comes to my mind is salt and pepper, which will never mix. Okay, they will always remain in a segregated place. You cannot do anything about it. It will remain as it is. But there are certain materials which, over a period of time, will have a tendency. Now, in those cases, at the plant level, they always keep those materials, even after mixing, under some kind of a gentle stirring. Finally, the material, when it is packaged, the process of final packaging of material and the process of mixing, that are to be brought as close as possible. So it is only in that way that you can prevent segregation. Because once your material is mixing, the thing is, you can, as you did mention, you add certain agents at times to affect those material characteristics, to affect the phase in which the material is. So there are different aspects that you need to. They would, as you said, you would need a binder, something which holds these materials, otherwise they would separate. So it all depends on the process and the formulation.
There is no fixed symbol for that.
There is, as I said, the field is so diverse that every process has to be treated separately. Every material characteristic has to be. There is nothing like a general rule. We could have specific cases, and every specific case will have a specific process for which we will have a specific. So what we would be doing over a period of 2 days here, we would be covering the segregation mechanism also. What causes segregation, why segregation happens. At a theoretical level, we would be discussing all of these. At a practical level, yes, each process then has to be studied, and the challenges related to those processes have to be addressed, one, from the point of view of formulation, from the point of view of equipment design, from the point of view of the layout, and the final objective that we are